Hello, good afternoon, students. I hope you all are fine. So we'll continue with the third module. I'm just sharing the screen. I hope it's visible to you. Is it visible to you? I hope so. So in the last class, we have seen with respect to accelerometers, we will continue that. So today we will see what we mean by seismic displacement sensing accelerometer. So what is the basic principle involved in it? When a spring mass damper system is subjected to acceleration, the mass is displaced and this displacement of the mass is proportional to the acceleration. Hence, a measure of displacement of the mass becomes a measure of acceleration. So if you see the figure, in this figure, linear seismic displacement sensing accelerometer is there. So you can see here damper is there, spring is there, electric displacement transducer is there. So what are the parts of a seismic accelerometer? It consists of a seismic mass is suspended from the housing of the accelerator through a spring. Apart from that, a damper is connected between the seismic mass and the housing of the accelerometer, and the seismic mass is connected to an electric displacement transducer. So there are two types of seismic displacement sensing accelerometers, namely linear seismic accelerometer and rotational seismic accelerometer. So both of the above mentioned seismic accelerometer work on the same principle as shown in the figure. So if you see the figure carefully, it is a rotational seismic displacement sensing accelerometer in which an electric displacement transducer, which is known as potentiometer, is there. Apart from there, dampers are there, spring is there, and a housing frame is there. So how it works? Operation. The accelerometer is fitted to the surface whose acceleration is to be measured. Due to the acceleration, the seismic mass experiences a displacement, and this displacement of the mass is proportional to the acceleration. As the mass is connected to an electric displacement transducer, the output of the transducer depends on the extent to which the mass is displayed. Hence, the output of the transducer is calibrated to give a direct indication of acceleration characteristic of the structure. So, how this accelerometer works? This accelerometer is first fitted to the structure whose acceleration is to be measured. So, we are interested in calculating the acceleration. Now, due to the acceleration, the seismic mass experiences a displacement, and this displacement of the mass is proportional to the acceleration. And what is happening is, as the mass is connected to an electric displacement transducer, the output of the transducer depends on the extent to which the mass is displayed. Okay. Next, the output of the transducer is calibrated to a given direct indication of the acceleration characteristic of the structure. So DVA spectrum, it is also known as tripartite DVA response spectrum. The response spectrum can be plotted with any of the three parameters, namely acceleration, velocity, and displacement. So we are interested in three factors, that is velocity, displacement, and acceleration. So this is known as tripartite response spectrum. Since these parameters are interconnected through the expressions 2.5 and 2.6, as given, all three parameters can be represented in a single graph known as tripartite plotter displacement, velocity, acceleration spectrum. So, what is the full form of DV spectrum? Displacement, velocity, acceleration spectrum. It is also known as tripartite DV response spectrum. So, what is happening in this type of spectrum is we are connecting or we are establishing a relationship between the displacement, velocity, and acceleration. So this is the figure. So the figure shows a tripartite plot of a response spectrum for two levels of damping. It can also be noted from the figure that the effect of damping on the response spectrum is greatest in the velocity sensitive region and is least in the acceleration sensitive and displacement sensitive region. So if you see the figure graph, it can be noted from the figure that the effect of damping on the response spectrum is greatest. So what is the effect of damping on the spectrum? It is greatest in the velocity sensitive region and it is least in the acceleration sensitive and displacement sensitive region. So velocity region is more subjected to what we can say earthquake and the least subjected to earthquake is the acceleration and displacement centralization. This is possible due to the fact that in logarithmic domain, this relationship boils down to a group straight line which are at 45-degree angles with line corresponding to spectral velocity. Spectral velocity already we have studied in the last class. So based on that, what is happening is you are experiencing more effect of damping in the velocity spectrum than compared to displacement or acceleration spectrum. It can be seen that there are three main regions in a DVS spectrum. So in a DVS spectrum, there are three main regions. First, the portion of response spectrum to the left of point period, it is 0.1 second, is almost constant and is more directly related to the maximum ground acceleration. So what is happening? The portion of the response spectrum to the left of the point period, that is 0.1 second, is almost constant and is most directly related to the maximum ground acceleration. Similarly, what is happening? The portion of response spectrum to the right of 10-second period is most directly related to the maximum ground displacement, which is also constant in that region. And the intermediate portion is related to maximum velocity of ground motion. So based on this information, a three-zone model of the triportrait can be postulated. So from the response spectrum, that is devious spectrum, what we are doing, based on this information, three-zone model of the triportrait plot can be postulated. These are a displacement sensitive region, that is long period region, an acceleration sensitive region, that is short period region, and a velocity region, that is intermediate period region. So different names are given depending upon the sensitivity received from the earthquake. These are the first is displacement sensitive region. It is a long period region. So the displacement, what we can space is projected to a long period region, whereas acceleration sensitive region is a short period region, and the velocity region is a intermediate region. So now use of response spectrum in earthquake resistance design. So what is the help of using response spectrum in earthquake resistance design? We will see now. A response spectrum is a plot of peak or steady state response, displacement, velocity, or acceleration of a series of oscillators of varying nature frequency that are forced into motion by the same vibration or shock. So what is happening? A response spectrum is nothing but a plot of the peak or steady state response, displacement, velocity, or acceleration of a series of oscillators of varying natural frequency that are forced into motion by the same base, vibration, or shock. So the resulting plot can they then be used to pick up the response of any other linear system given its natural frequency and oscillation. So one such use is assessing the peak response of buildings to earthquake. So what we are doing, we are assessing how much peak response a building is experiencing, how much earthquake it is experiencing, we are calculating. The science of strong ground motion may use some values from the ground response spectrum calculated from recordings of ground surface from seismograph from correlation with seismic data. If the input used in calculating response spectrum in steady state periodic, then the steady state result is recorded. Damping must be present or else the response will be infinite. For transit inputs such as seismic ground motion, the peak response is reported Some level of damping is generally assumed, but a value will be obtained even with no damping. So now what we are doing, response spectrum can also be used in assessing response of linear system with multiple modes of oscillation. So response spectrum is not only used to determine the earthquake resistance criteria, but also it is used in assessing the response of linear system with multiple modes of oscillation, multiple degree of freedom system, although they are only accurate for low levels of damping. Modal analysis is performed to identify the modes and the response in that mode can be picked from the response spectrum. These peak responses are then combined to estimate a total response. A typical combination method is the square root of sum of the square SRSS if the model frequencies are not close. So SRSS method is widely used as a response spectrum method to assess the intensity and magnitude of an earthquake. So what this stands for? Square root of sum of square. The result is typically different from that which would be calculated directly from an input, since phase information is lost in the process of generating the response spectrum. The main limitation of response spectrum is that they are only universally applicable for linear system. Response spectrum can be generated for non-linear system, but only applicable to system with the same linearity. Although attempts have been made to develop non-linear seismic spectrum with wider stage application. The result of this cannot be directly combined for multiple mode response. So this completes our second module. For equivalent method, one more thing is that I will share with you. Right. In the module 2 only, but equivalent lateral force that we can study, I will just share with you. Equivalent lateral force method. Okay. So I'm sharing the screen. Hope it is visible to you. So till now we have studied about response spectrum method. Apart from response spectrum method, one more method is there that is known as earthquake lateral force analysis. So the design lateral force shall be first computed for the building as a whole. So earthquake analysis, whenever we do, we need to calculate the lateral force acting on the building. So the earthquake lateral force analysis is very important. So the design lateral force shall be first computed for building as a whole. The design lateral force shall then be distributed to the various floor level. See, generally G plus 2, G plus 3, G plus 5 buildings are more prone to earthquakes because as the floor increases, the strength of the building decreases. So the design lateral force shall be then distributed to various floor levels. So the two commonly used procedure for seismic design lateral analysis are equivalent static force analysis and dynamic analysis. So first method is equivalent static force analysis. The concept is a dynamic analysis into partly dynamic and partly static analysis for finding the maximum displacement. It is restricted to a single mode of vibration of the structure. Equivalent static lateral force analysis is based on the following assumption. So before studying the equivalent static force analysis, we need to make some assumptions. So what are the assumptions? First assumption is the structure should be rigid. First assumption is we are assuming the structure to be rigid. It is not flexible. Next, assume perfect fixity between structure and foundation. Don't get confused between the first and second assumption. In the first assumption, what we are trying to say, we are assuming the structure is rigid. Your entire structure we are assuming it to be rigid. But in the second assumption, what we are trying to say, assume perfect fixity between structure and foundation. As you know that a structure consists of substructure, superstructure and all. What we are assuming? We are assuming perfect fixity between the structure and the foundation. During ground motion, every point on the structure experiences same acceleration. So what is happening during ground motion? Every point on the structure experience same acceleration. So what is happening during ground motion? When the ground moves, every point of the structure experience same acceleration. Normally we think that different floors, people different maybe experience different acceleration, but what it is in reality, during ground motion every point on the structure experience same acceleration. Dominant effect of earthquake is equivalent to horizontal force of varying magnitude over the height. What is happening? Dominant effect of earthquake is equivalent to horizontal force of varying magnitude over that. See here, the effect of earthquake mainly depends upon the intensity and magnitude of the earthquake that is acting in horizontal direction or lateral direction. Approximately determines the total horizontal force. Total horizontal force is nothing but your base shear. So approximately we are determining the total base shear on the structure. So what are the limitations of equivalent static lateral force analysis? In the equivalent static force analysis, empirical relations are used to specify dynamic inertial forces as static forces. So what is the limitations of equivalent static force analysis? First we have seen the assumptions. Now coming to the limitations. In the first limitations, in the equivalent static force procedure, empirical relations are used to specify dynamic inertial forces as static forces. So what is the limitation of equivalent static force analysis? In the equivalent static force analysis, what we are assuming? Empirical relations we are assuming, which are used to specify dynamic inertial forces as static forces. Although the forces are dynamic nature, we are assuming in that to be static force for our convenience. These empirical formulas do not explicitly account for the dynamic characteristic of the particular structure being designed or analyzed. As we are making an assumption that the dynamic forces are static, then the empirical formulas which we are using, they may be good, but they may not be accurate in determining the dynamic characteristics of particular structure being designed or analyzed. These formulas were developed to primarily represent the dynamic behavior of what the so-called regular structures. See here, whatever things we have done based on RPA using IS books and all, it is an assumption. It may not be considered as a final outcome. So there may be some possibility of error. Structures that are classified as irregular violate the assumption with empirical formulas used in the equation. See here, for our purpose or our convenient, we are assuming the building to be regular building, symmetric building, asymmetrical building. But in reality, this type of cases may not arise. So it is also a limitation of equivalent lateral force analysis. Now you will see step-by-step procedure for equivalent static force analysis. So the first step one is, depending on the location of the building site, identify the seismic zone and assign zone factor. So the first important what you can say step of equivalent static force analysis is, depending upon the location of building site, what you have to do, you have to identify the seismic zone, zone 2, 3, 4, and 5, and you have to assign a zone factor Z. Z. Use table 2 along with seismic zone map of annexure IS 1893 2002. So this codebook IS 1893 2002 can be used as a tool for designing earthquake resistant structure using equivalent static force analysis. So using table 2 along with seismic zone maps or annexures of IS 1893-2000, we are assigning the zone factor. Next, compute the seismic weight of the building. In the second step, what we are doing, we are calculating the seismic weight of the building. As per the clause 7.4.2, IS 1893-2002, seismic weight of floors we are calculating. Next, as per clause 7.53 IS 1893-2002, seismic weight of the building we are calculating. Next, compute the natural period of the building. TA, natural period of the building, TA is calculated. As per clause 7.6.1 or clause 7.6.2, IS 1893-2002, as the case may be. So depending upon the cases, we have to use the respective clause 7.61 or 7.62, and we have to calculate the natural period T of the building. Step 4, obtain the data pertaining to the type of soil conditions or foundation of the building. So obtain the data pertaining to type of soil condition. The soil may be different, medium soil, soft soil, hard soil. So how we are calculating or evaluating the data? We are obtaining the data pertaining to soil conditions of the condition and assigning. Suppose assign type 1 for hard soil, 2 for medium soil, 3 for soft soil. This is also very important step. Now, using time period TA and soil type 1, 2, and 3, we're calculating the spectral acceleration SA by G. So for this, what we are doing, what we are using figure 2 or corresponding table of ISO 2002. We're calculating SA by G. Next, assign the value of importance factor. This is also a very important criteria. What we have to do, we have to assign the importance factor I depending on the occupancy or functionality of structure. So for assigning the importance factor also, we have to use clause 7.2 and table 6 of IS 1893 2002. Now in the step 7, what you have to do, assign the values of response reduction factor depending upon the type of structure. Next step is response reduction factor. How we are calculating response spectrum factor? Depending upon the type of structure, type of soil. So for that, clause 7.2 and table 7.5, 7.6 of table 7 of IS 1893 2002 can be used. In the step 8, knowing Z, SA by G, R and I, compute design horizontal acceleration AH. So from the data which we have obtained from the earlier step, we are calculating horizontal acceleration coefficient KH, which comes out to be Z into SA into I divided by 2GR. This is as per clause 6.4.2 IS 1893 2002. If can remember, it is well and good. If not, it is available in the code book. Now, step 9, using AH and W, compute design seismic base shear VB from VB equal to AH by W. So using AH, just now in the step 8 we have calculated AH, that is design and horizontal acceleration. So using that AH we are calculating VB. So what is VB? Seismic base shear. So what is the formula for VB? VB equal to AH into W. So this formula is also available in the IS 1893 2002 clause 7.5.3. Next step 10. Compute design lateral force QI of ith floor by distributing the design seismic pressure VB as per the equation. So in the step 10, what we are doing, we are computing the design lateral force QI of the ith floor by distributing the design seismic base shear VB as per the equation. So what is the equation? QI design lateral force equal to VB into WI into HI square divided by summation of Wj into Hj square. Limits are from j is to 1 to n. This formula is also available in clause 7.7.1 IS 1893 2002. So I hope the equivalent lateral force method is clear to you. Now, dynamic analysis. Dynamic analysis is classified into two types, namely response spectrum method and time history period. So dynamic analysis, it is again further divided into two more methods, response spectrum method and time history method. Time history method of analysis, when used, shall be based on appropriate ground motion and shall be performed using accepted principle of dynamics. So response spectrum method of analysis shall be performed using the design spectrum method specified in clause 6.5.2 or by specific design spectrum mentioned in clause 6.5. I see here, all these are methods of analysis of an earthquake. So this method should be used based on IS codes only, 1893, 2002, different clauses. It cannot be used individually by you and me. When dynamic analysis is carried out either by time history period or by response spectrum method, the design base shear computed from analysis VB shall be compared with the base shear calculated using a fundamental TA or VB dash. What we are trying to say, जब भी आप डायनामिक एनालिसिस करते हैं तो मे बी बाय टाइम हिस्ट्री मेथड और रिस्पांस स्पेक्ट्रम मेथड द डिजाइन बेस शेयर computed from dynamic analysis VB shall be compared with a base shear calculated using a fundamental period dA or PV raised to where dA is as per clause 7.6. If the base shear obtained from dynamic elastic VB is less than the base shear computed from equivalent lateral method VB, what is happening? If suppose the base shear obtained from dynamic classes, we calculate base shear from dynamic classes, it is VB. If it is less than the base shear computed from equivalent static method, VB dash, then using TA as per clause 7.6, what we are doing as per clause 7.8.2, all the response quantities, for example, member forces, displacement, and strain will be computed using the ratio VB bar by VB. So this also you should remember whenever we are calculating the base shear with respect to dynamic analysis or time history method, if your VB value is less than VB dash, so you should multiply this with ratio VB dash by VB. Now we will see what is the step-by-step procedure for response spectrum method. In the step one, depending on the location of the building site, identify the seismic zone and assign zone factor. So it is also similar to your equivalent lateral force method. Here also what we are doing, depending on the location of the building site, which type the where it is located, whether it is located in soft soil or the soil is hard, depending upon the location of the building site, we have to identify the seismic zone, zone 2, 3, and 4. And based on that, you have to assign zone factor. So different zone factors are available in different codes. Now use to table 2 along with seismic zone maps of annexure IS 1893 2002. So in the second step, we are calculating the seismic weight of the building W as per the number of floors WI. In the step three, what we are doing, establish mass and stiffness. Mass we are calculating with the help of M, and stiffness we are denoting with K by tracing of the building system of masses lump over one another. In the fifth step, what we are doing, computing modal mass Mk for mode K using the relationship with N being the number of modes considered. So the formula used is Mk is equal to summation of Wi phi q divided by G into summation of modal K. So in the last step, what you have to do, you have to compare the modal participation factors PR mode by using the following relationship where n is the number of modes considered. So it is also available in IS 1893 2002 Pk equal to summation of Wi into phi k divided by summation of Wi into phi k square. In the step 7, what we are doing, we are computing the design lateral force QIK at each floor in each module. That is for ith floor in mode K using the following relationship. QIK is equal to AH into K, phi IK by PK into WI. In the last step, we are computing the storage shear forces in each mode using the formula VIK is equal to summation of I plus 1 and QIK. Ninth step is compute the storage shear forces due to all modes considered. Finally, in the 10th step, we are calculating the design lateral force in storage using the formula F roof is equal to V roof and Fi is equal to Vi minus Vi plus 1. So this is as per clause 7.845 F equal is also available in IS 1893 2002. So this completes our theory part. In the next class, we will see the problems on it. One more thing you have to remember is whenever you solve a problem on earthquake resistance structure, you should be familiar with the use of IS 1893 2002. I will share the IS code with you. If you have any queries, you can just place your queries in the comment box. Also, you can contact me at nadeem@k1.university, or even if you have further doubts, you can call me in the evening time at 8553171859. I hope you will have a nice day. Thank you. We will finish this session. In the next class, we will see problems of it or numerical problems on how to solve this.